All right. Welcome to my webinar on using two transformers to double voltage gain in an ultrasonic transducer drive circuit. My name is Hussein Shakani. I am the founder and lead consultant of my company, Ultrasonic Advisors, and this is my webinar. Today, during the presentation, I'm going to describe the problem with off-the-shelf transformers. And then we will go to how to use true transformers to double voltage and how to use multiple transformers. That might be been a better topic to do things you normally would not have ever been able to do, I think, without using more than one, and other practical notes on how to do this. So as you would expect, we'll go over equipment, the turns ratio, like characterizing the transformers themselves, what kind of wiring you need for doubling voltage, and how do you connect them incorrectly. I'll describe that, and I'll describe the results too. Today's going to be a simple webinar, like it'll be shorter than some of my previous ones, and I'll also describe why. Why would you do this? I'll give you some examples when it would be very, very useful to use more than one. But before that, I will introduce my company, Ultrasonic Advisors. So I provide ultrasonic transducer consulting expertise to any company who needs it. So I provide both hands-on simulation and consulting and training work for companies developing transducers such as bolt-clamped Langevin transducers, other types of power ultrasonic transducer sensors, atomizers, surgical transducers, motors, um, um, pulse echo devices, for example, different various medical devices and portable transducers. So I've done things like optimization, troubleshooting, circuit development, hardware, so a lot of different activities. And I will even come to you if the price is right. Yeah, please contact me through my website and follow the links, and you'll see how to do that. So let's get into the topic, which is the equipment. So what am I going to use to demonstrate the use of multiple transformers? But before that, why would we use multiple transformers, and what do we get out of it? So if you notice here, many amplifiers are stereo. So okay. Firstly, many of the kind of amplifiers that you can use for ultrasonic transducers are from the audio area, and for audio, we often have stereo amplifiers. So stereo amplifiers means two channels that are separate. Stereo. I'm sure you know that. Yeah. Um, so like this one right here that I mentioned here. So there's two and I'm gonna change the color so you can see what I'm writing and reduce this length. So this is two 50-watt amplifiers, but this is in a stereo configuration. So, but what if we wanted to drive one transducer with 100 watts? How would we connect those two together? Um, well, and how do we get that full power rating of this specific amplifier board or other amplifier chips you might get? How do you do that? Well, you can use two transformers, and I can show you how to hook them together. In another case, what if I have these 100-watt mono, so that's single channel. So we have a 100-watt amplifier boards. How do we hook those two together to get 200 watts? Because you wouldn't, if you keep adding transformers, you're not going to increase the power output of your electronics. You will get twice the voltage. Sometimes when you mean twice the voltage, you get square of the power. So usually what happens, and this is I think an important thing to note. So if your voltage like V power equals I squared R, and then if you were just talking a resistor, V equals IR, and so if we want to substitute V squared over R squared, R equals power. So if you're looking at power in terms of watts, it equals V divided by R. V squared divided by R. So power will go up. Let's just use a very simple resistor model. If you change voltage by 2, you'll increase power by 2. So note that you won't be able to use the full voltage range of your amplifier per se, unless you don't have very good matching. So this, in effect, by increasing voltage, basically you're matching your power needed by your transducer. So it's not exact. You're not power doubling. You're never going to get more power from your amplifier than you originally had, but you can utilize and allow you to get the maximum power out of it by effectively doubling that voltage, causing more current to flow as a result, and hence more power. So you can get up to 200 watts. You could also double the voltage, but notice you'll always lay under those 200 watts, even though doubling the voltage would raise the power, by a factor of itself, like square would square the power, but it won't. But that won't happen because we're assuming that your amplifier wasn't perfectly matched to your transducer anyway, or even your transformers. So the two things. So we can join more than one amp. We can do stereo to mono, so you can get the full power or full voltage spectrum from one. You could also just double the voltage. It also helps you match the impedance, because many times we'd like to use stock transformers even for testing or as experiments. But they have specific values, and they do vary, but it would be great, especially if you had space on your board, to use more than one component to get the correct voltage output that you desire, but still be operating in a very stable format. So you don't have you can cheaply and easily attain a 1-to-4 ratio. Transformer. Well, what if I want 1-to-8, basically, and that specific device isn't available for the price and the size format or whatever you need, then you can get 2 and hook it in the way that I'm going to speak about. So let's continue to the equipment that I'm going to use to demonstrate and also characterize. I'm going to be using the Analog Discovery 2 bundle, and you can use Analog Discovery 3 as well. That's fair game there. But basically, I'm also going to be using this breadboard attachment here and the Analog Discovery itself. So those are, and I'll also use a breadboard itself. So what I'm going to use here, so there's a couple of audio transformers. I'm going to be using a small one. They're just easy to fit on the breadboard for my testing purposes. I could have ended up using, there's no reason I didn't use something like this, this transformer here, which has a ratio 56 turn. That's a pretty good turns ratio there. 7 turns, and this is 56. Oh, that's great. Well, that's really high. Anyways, you probably don't want that high, because then your output impedance will be too high. So in this case, it's advertised as a 1300 to 8 ohm voltage amplification transformer. They're really small, and generally, the smaller you get, the less power you can deliver. However, that's not exactly true for small transformers. For higher frequencies, for higher frequencies, you do get increasing efficiency with the higher frequencies. So your transformers don't have to be as big, but they're not exactly the micro, really small ones that I'm actually using today. But this could still be very useful for like a sensor. If you wanted to output a sensor, probably the sensor would not have a low input impedance, but if it did, you could use that. But yeah, we're mainly talking about actuating transducers, and this is the LCR meter that I use. And remember, the reason I use an LCR meter, it's just handy in comparison to using the Analog Discovery or a traditional impedance analyzer, but also in case you do want to measure the capacitance and the dielectric loss for low dielectric loss samples, like hard PZT transducers, then you need to have a dedicated LCR meter to measure those low phase values, basically the low loss levels. So let's continue to the turns ratio. So how do we calculate that and characterize our transformer before we get started? So at 10 I set my impedance analyzer, or sorry, my LCR meter at 10 kilohertz, and I measured the impedance on the input and output side, or the one side and the other side. There's no difference between the input and output. It's just that one side is low impedance, low number of turns. One side is high impedance, higher number of turns, higher inductance. Or so this is 243 ohms. This is the low side, and 42 degrees. 42 degrees, which means it is mostly resistive at this point. So the minimum load that that if you hook up your amplifier to this, the minimum load it's going to see is 243 ohms. So that's important to know, because although you won't find amplifiers with like high output impedance, like 100 ohm output impedance, but this transformer itself is going to eat some of the current already, but it's not too much. And what I wanted to go, I forget why I was skipping around here. Yeah, so in the secondary side, we have, or the high impedance side, we have 6.5 kilo ohms and 47 degrees. Now these are, I could have done the inductance ratios and things that probably would have been more accurate, especially given this large phase angle here. But it ended up still remaining true, because the phase angles were approximately similar. So whatever amount of this impedance was actually just due to the inductance, it got kind of conserved, you could say. So by virtue of by virtue of consistency, it still worked out to be, I still was able to calculate the turns ratio accurately, and that also turned out to be verified when I did the waveform excitation and then measurement. So how do you do turns ratio again? What was that thing? Oh, so I'll show you. You have the L1 and L2, so 243 ohms, 6.5 kilo ohms. Here's the impedance ratio, and the square root of the impedance ratio is the number of turns. So there's 5. It's 1 to 5 basically. If you look at this device, 1, 2, 3, 4, and then 1, 2, 3, 4. So it's like a 1, 2, 5. And this is the low Z, and this is the high Z. And those markers are actually on the specific, if you were buying this transformer, it has markings on it that say high Z and low Z, and the one that I had was black, as you see. And there are no questions so far, so we'll keep going. So how do you double the voltage? One of my skills as a consultant is making something that's short very long. That's how I stay in business. I'm just joking. So how do you double the voltage? Obviously, if you just directly hook up the power source here, you hook up here and you kind of ground this side. Let's say this is also referenced to ground. If you put 5 volts, sinusoidal 5 volts here, you'll get 25 out here, right? Or if you put 1 volt, you'll get 5 volts. So that's something you'd know. But let's confirm that at a frequency we all know and love, which is 40 kilohertz. But before that, this is just the wiring diagram. But I will show the kind of semi-technical sketch here. So the input side. So these are the two transformers. So transformer 1 and 2. So this is the 1 to 5. 1 to 5. And this side is connected in what you would normally see as parallel. And this is series, connected in series. So what you would say if you had another way of drawing this, I'm just like your that's actually not correct. So if you were to draw the input coils, the input coils would look like this, and then the output coils if you were just drawing them as inductors, which why not, right? The output coils would look like that. So if you simply took these, I'll just do highlighting and erase it. You took these and put them there, and you took these and put them there. This is what it would look like. So these are actually in parallel, and the secondary side is in series. And what that does is it draws more current from the primary side, and it produces more voltage from the secondary side because these voltages add, and you can connect these because they're floating. The secondary side is floating. So because it is floating, you can connect it. You can connect ground here if you'd like to. I don't know why you would. Usually you can connect ground to here. You can connect ground wherever you'd like. Then this voltage will be referenced to ground, and that's actually what I did. Actually, no, I didn't do that, but you could do that, and that would be just fine. Or for a reason I'm not aware of yet, you could actually put this middle part as ground, and that probably would be useful if you were driving some type of other MOSFET circuit or something. That could be useful if you had also some type of oscillating, but two oscillating devices there. But usually you would want to put one at ground if it matters, or just leave it floating. Why not? But you could easily use one of those 2 times 50 watt stereo amplifiers to get your full 100 watts out of here. Or what actually happens a lot is you get like a 12 volt amplifier, and you want to double the voltage. You can use 2 transformers, or you could obviously use more than one amplifier and connect the amplifier. So this could also work in another way, where you have another device here. So let me just erase this. So if you had, this is going slow. All right, so you had another here, and then you had another. You had your other source, or your other. I'll get this in red again. Just keep the colors consistent. So you had your amplifier. You had your amplifier 2 and your amplifier 1. Now you can effectively double the power that you can deliver, and that's awesome. It's almost like if you were driving, if you had like 4 piezo crystals and you were driving two with each amplifier. You would not do that, but you actually could, and you get isolation, and it all worked just fine. That's pretty much the same thing you're doing here. You are driving sometimes we understand piezo crystals a little bit better, which is not typical for the rest of the world. The rest of the world usually understands probably transformers or other things a bit better. But so if you had a stack of 4 crystals, you could drive that's, and then we'll just, black doesn't work, so we'll do white. And then we'll do red. Why not? So if you have these being driven, this is a stack. So you could have like these being driven from one amplifier and these being driven from another one, let's say, and this say you keep this at ground. It would be kind of similar to using those 2 amplifiers or 2 transformers. So, but this is obviously making everything, all the electrical wiring, a lot easier. So this is the circuit. As you can see, the input sides are connected. So this is the low Z. This is a low Z, and this is the high Z side. And I just put these wires here as like the input. These are the input sides, or this is both the output sides, where these are connected in parallel. So the driver is seeing a lower impedance, and these are connected in series, where your transducer would both be, it's driven by a higher output impedance, but typically, like, you don't perfectly ever match. Typically, we don't perfectly match our transformer or drive circuit to our transducer. That would cause way too much interaction. There's typically some amount of unbalance. So many times you could probably easily get away with having 2 transformers, and now suddenly you've doubled your voltage capacity, and you've quadrupled your power capacity of your drive circuit, assuming your amplifier can support that power. It's always dependent on that amplifier. However, I'd like to mention some amplifiers are limited by current. So there's a specific amplifier that's limited by 2 amps. It doesn't necessarily care what voltage you use in its output scheme. I think the maximum for that one would be like 24 volts or something. It has 24 volts. So if you had your sinusoidal voltage go from like 0 to 24, it doesn't care as long as you stay within those 2 amps. But suddenly, you would probably able to use both the channels and work in a different voltage current regime. So you need the maximum voltage at the maximum current in order to achieve the maximum power. So this can help you with that. So let's go with the results. So this is like this is very basic, mind you. So let's do the results. In the orange, we have the low Z side. And the blue, I should probably make it the same color. We have the high Z side. And this is a 1 transformer. This is single, which is basically, I'll just draw really fast. This is this. We have 1 transformer. The input, the low Z input is 1 volt. And the high Z output, it's easy to see, it's 5.4. So we have 5.4x the voltage at 40 kilohertz. And the frequency has an effect on the efficiency of a transformer. As you go higher in frequency, now you're losing less to the resistance because the inductive impedance is now increasing. So you do have frequency effect, and now double. So what's double again? Somebody remind me from the crowd. Okay, that's 1, and I'll just draw it this way because you already have that good diagram on the other side. That's 2. And now we are driving. There's no line connecting it. Now we're driving another 1 and the output side, and we are connecting these, and we're measuring from this side. So this is the high Z, and this is the low Z side, and I just showed that. That was the whole point of the presentation. Moving my head to the side here on the video. Excuse me, this head. Okay. So we have 1 volt, and now we have 1 volt on the low Z, and now we have 10.8. So now we have effectively doubled the voltage. Now there's no load on this, so it's not like it's not a perfect experiment to show you what would happen in all cases, but in general, one of the premises, you can use this for impedance matching, but one of the premises here is usually your amplifier is not perfectly matched to your transducer, so many times you're massively underutilizing your amplifier. So this gets you a whole lot closer, because again, you double, you square your power when you double your voltage. In general. So what else do we have here? There's a couple of things, a little bit not the best organized. So this shows the input and output based off of these two transformers. So this is the input output ratio. So this voltage here, it shows about 10.8. So 10.8 volts, and I kept the input at 1 volt. So the input we're putting in 1 volt. So whatever this ratio. So as you can see at this frequency here, around 300 kilohertz is a resonance. So watch out for those things because coils resonate. So you're not just going to use this now at any frequency here. And now it's a resonator circuit increasing the voltage. It's not just the transformer function itself. And as you go higher in frequency, you'll start to get that resonance effect. But at, like, let's say, and this is 30 kilohertz, this is 40, 50, 60, 70 for the specific transducer. You're probably good, even to a higher frequency, but you'll have to note how that's working for you. What was I doing here? I think this was just none of you. So we're basically done. Show here. Okay, so let's just take a look at this one real fast. La, la, la. Yes. So yeah, I think we'll just call it a day. I just didn't organize those ones. So back to the original topic, and I'll just kind of write this to summarize. Let me zoom in here. So we can use two transformers. We can use the low Z in parallel and the high Z in series. We get twice the voltage, and we can use this for excuse me here. All right, this wants to take me up. We can use this specifically for increasing so using 2 amps. This is an increase power. We can use a stereo amp to 1 output, and that's also to increase power. And we can also just plain use multiple amps. Again, well, that's the same as the first, use 2 amps, but and we can also just plain increase voltage, increase voltage. That just like basically better use of the amp on hand. So you can just easily double your voltage without having to like dig through the manual. You could use, there's going to be a variation between the amplifiers, so you can't just string together like 20 amplifiers and you have like a very linear 100 volts 200 volt system, but it's similar to that case. And there was something else I wanted to mention. Oh, I did the other experiment. I did one more experiment. And I wanted to show that before we left here. This is the hey, why not? Let's try it. Experiment that I did here, and drop my pen. So in this case, I don't know what the right term is, but I'm just gonna call it cascade. Cascade. I think it's the right way to spell it. So I did this, which is what you might be tempted to do. So this is low Z, high Z. Low Z, low Z, high Z. No, again, these things won't work on a sensor because the sensor doesn't have any drive power. So you probably I think depending on the sensor itself, though, actually, you may not have enough current that's going to flow to actually power a transformer to improve it. Although sometimes I think on microphones and stuff they use it, so I don't see perhaps why it wouldn't work for a piezo. But this is like 1 to 5. So we think we have a voltage gain of 5x, right? And then we have again 1 to 5 here. So why not just do this and we increase our voltage again by 5? So if our initial gain was 5, then we should have 25 at the end. Normally I was like, saying, hey, 10 is great, 10x is great, but this case you should have 25. So in a cascade format, actually, even open circuit, so there's no load on the transducer, you get 16 or 17 times. And this number was varying a little bit based on how I pressed the transformer in the socket because it didn't seem to fit very well. But at 40 kilohertz, you had 17 times. So, what is this better? No, it's not better, and I don't recommend this simply because now the high Z and the low Z of the transformer are explicitly very much unmatched. It is giving you 25 volts, or in this case 16 or 17 times more. So instead of originally we were at 5x, and then with the I'm just call it the D. I'm just gonna call it the D configuration. We had 10x, and with the cascade, we had, let's just make it 20x. But the thing here is the power delivery goes down. So our ability to deliver power goes lower. Even though the voltage is higher, we will not be able to maintain that voltage because the power consumption, the current needed to drive this transformer, to drive this one, to drive that one, I didn't exactly know how to evaluate the efficiency of Cascade Transformer. I probably could have done it the same way by shorting the outputs and stuff, but I think it's going to be very low efficiency. So this is high efficiency. What do they write? Sometimes people write efficiency with this N thing, and the second case is also high efficiency here, but this is low efficiency. This is low efficiency, but it is technically higher open circuit voltage. And with that, I would like to finish this presentation, and I'll finish it on this side here. I'll finish this presentation, and I'll ask if there's any questions. So stop the recording.